Now is actually finish up the different parts of that equation. So as we were looking at the heat balance equation, one of the other variables on here was R, or radiation. So radiation, very simply, is energy waves. Again, a lot of times electromagnetic. We could talk about light waves as well in this one, are part of that spectrum. Uh, Human body is going to absorb the radiation that falls upon it, just like most objects are going to. And really what this does is this heat or light particles, they're absorbed by the body. Uh, in molecules, as you hit more light upon these ones, it is going to absorb this one. And again, in reality, it has to do with the kind of changing the energies in those different electrons and kind of moving around closer to the nucleus. Again, molecules that we are made up of, again, are going to absorb and radiate this a little bit differently than actual atoms would. They're going to vibrate more or less. The more heat or more radiation hitting them, the more they vibrate. Less radiation on them, the less are going to vibrate. So we have photons coming from the sun at light speed. They are hitting the skin and being absorbed by it and are going to cause an increase in the vibrations of these molecules, and that is going to warm the body. These molecules also vibrate somewhat on their own, and as there is not light hitting them, or there's less in the environment than there is in the body of this radiation, the body can also radiate some of this vibration, lose some of the vibration as heat, and lose temperature, lose temperature that way. Again, depending on the type of electromagnetic radiation we're talking about, we will feel it or not. Like it says here, long wavelength radiation, we don't see it and you can perceive it as heat. So a lot of times they talk about infrared. A lot of times with infrared cameras you can see heat. That is because the heat is actually a longer wavelength electromagnetic form of energy. But you've probably felt this like on a pan or other stuff like that. You can't see the heat coming off the pan, but you can put your hand above a pan and you can tell that it's hot. We know the shorter wavelengths of the electromagnetic spectrum are part of that visible light. So those reds and yellows and blues, those would all be part of the electromagnetic spectrum that is actually visible to us. What we're going to see, though, is there's a number of factors that are going to affect radiative heat loss or gain. Again, the biggest contributor to a lot of this is going to be the sun. It can be the sun hitting us directly, it's kind of diffusely hitting the atmosphere, and that's getting reflected onto us. Or you can also talk about the ground or the water and hitting that and having those radiative photons bounce back up to us. Again, also ground can absorb that radiation and then emit it later on. And also the sky. We, from the body, are really just going to radiate heat from the body. So this kind of gives you the idea right here. You can have diffuse heat coming from the basic radiation on the atmosphere, and that heat in the atmosphere is going to get radiated to us. You're going to have the sun hitting you directly, as well as light rays hitting that ground and being reflected back up to you. Again, anything that's hitting your body in terms of these photons is going to be absorbed. And again, just like everything else we've talked about, there's a number of factors that are going to influence this radiative heat gain. Again, the bigger the difference between the skin temperature and the environment, the more we're going to absorb. The more surface area we have, the more we're going to absorb. And again, that is also kind of figured in this clothing. If you have clothing that is not, if you don't have as much clothing on you, you can absorb more into the surface of the skin. If you are wearing darker colors, they tend to absorb more radiation than the light colors. If you've ever been out on a hot day, wearing a dark shirt is going to heat you up much quicker than wearing a light colored shirt. Those are some other factors that are going to influence heat gain. The smoother the surface of the skin or the clothing, the more you're going to absorb that. And again, as we get higher up in altitude, there is less atmosphere over you, so you have more direct radiation hitting you. As well as at those higher altitudes, a lot of times there's going to be snow and ice, and these are going to be things that reflect solar radiation much better than the ground that's bare. So it will reflect that on you versus absorbing it. Anything that makes the air thinner, again, less density in it, is going to let more get to you, so air pollution again. And again, anything going the other direction, again, wood, decrease radiative heat gain. So wearing light colors, being closer to sea level, having rough textured surfaces on the skin and clothing, all these things that make it harder for the light to be absorbed. So, and really the last thing I want to talk about on this heat balance equation is this idea of evaporative cooling or evaporative heat loss. So this is heat transfer due to the evaporation of sweat. So we sweat, it's not the sweating that cools you down, but it's actually the evaporation of the sweat that is going to cool you. So when you take a liquid and change it to a vapor, this is going to take heat in order to get that transition change to happen, and it's this evaporation that is going to pull heat from the body at the skin surface and dissipate it away from the body. Like as I was saying, it is the evaporation of sweat that is the cooling, not the production of the sweat, which is part of the reason if you have been doing something, you stop and then you get a cool breeze blowing across you, that increases the decreases the rate of evaporation, which is going to a lot of times cool you down much quicker. So like when you get out of the water on a windy day, you get cold way easier than you do if it's a really stale air day. And again, when we start talking about trying to lose heat in hot environments, this is going to be that big thing. It's really this evaporative cooling when we're talking about at hot temperatures. So in the heat, in high humidity, this is going to be our best way to try to dissipate heat and not gain core heat. So we have what is called insensible or evaporative heat exchange. And this is the evaporation of that water on the body's surface, changing from a liquid to a gas. That, like I said, requires heat. It's extracted the heat from the surroundings, so it might be the air, but it's also going to be the skin. And the more we absorb from the skin to get rid of this, the more we can actually cool the shell. And with conduction, that means we're also going to be cooling the core a little bit more. So the amount of evaporation, again, it's all about concentration gradients. Again, if it's not a humid day, we can lose more lose more heat to the environment. When we're on days where it's really high humidity, there is not as big a concentration gradient. There's more water in the air, so it becomes more difficult to evaporate that liquid and get it into the environment. So like I said, this evaporative heat loss is that insensible perspiration. The insensible perspiration is that just sometimes we do lose some water through our skin. So just being out there in the heat, even if you're not having thermal sweating, you will lose some water through your skin. Not a lot. Our biggest water loss a lot of times is with that thermal sweating. We can also have non-thermal sweating. So that nervous sweating when you're just getting tense and it's that sympathetic nervous system kicking in, sometimes will trigger some sweating. Again, this is not really for evaporative cooling. The other thing we'll see is water losses sometimes through evaporation from the respiratory tract. We lose some through evaporation there. This is much more common when we're in a less humid environment. So when you're at altitude where there's less humidity in the air, you tend to lose more. Also, the cold air cannot hold as much humidity, so we tend to lose more water through the respiratory tract in those conditions. In both those cases, it's even much greater loss when you are actually exercising. Normally, at rest, due to insensible loss, it's really about 30 mils an hour. But when we get into a high temperature environment with strenuous exercise, we can get up to sometimes 2 liters per hour of water loss, which again, that is going to become an issue rather quickly if you're not replacing that lost water. And factors that are going to influence this or increases evaporative heat loss, again, the biggest thing with a lot of this is having that good gradient. So if you have water on your skin and it's evaporating off, the less vapor there is in the air, the easier it is for that heat to vaporize the water on your skin and get it into water vapor in the air. And again, less humidity in the air is going to increase that pressure difference. Like I said, relative humidity, the higher the humidity, the more difficult it is to evaporatively cool. Always surface area, if we have more surface area, and if you think about the areas where you sweat a lot of times when you're working out, it's the back, the chest, a lot of these really big surface areas that are going to help cool the body. Also, dimensions of the body and shape of the body play a role in this. Again, if you're bigger through the torso, there's not as much surface area there, so longer limbs and legs relative to your body, your actual core, is going to be increasing your ability to dissipate heat. That's one of the things we'll see as we talk about exercising the heat a little bit. That's part of the reason that a lot of the Kenyans and the Ethiopians tend to be the vast majority of the elite marathoners. It really has to do with the fact that they can dissipate more heat. They tend to, as a population, have longer limbs relative to their torso size than a lot of other populations. Again, the less we're covering the body, the better this is going to be. So a lot of times in the heat, that's part of the reason if you're working out in the heat, you'll a lot of times wear a tank top or other stuff there. It's going to allow you to get more surface area to that environment, let you cool off even more. Obviously, if we sweat more and we're putting more fluids on the surface, this is going to increase that heat loss through evaporation. The more dilute we get the sweat, so the less salt that's in there, it increases that thermal conductivity. It makes it so it pulls more heat away when it's evaporating. Again, more body surface area that is being covered with the sweat. And then also, again, increases in altitude tend to decrease humidity in the air, which is going to allow for that air to be able to take on more moisture. Anything that increases the air speed going across the body as well is going to increase that evaporation, and you can help get rid of that. Exercise will also do this. You're moving through your environment a little bit more, but again, there is some balancing here in that exercise and muscle contraction is going to generate heat. So while you're moving through your environment, it is going to help cool you a little bit more, but you're also creating more heat through metabolic work. And it also increases in core temperature are also going to make it easier to have more evaporative heat loss. But again, we're trying to dissipate that core temp. So as you're doing something, your core is going up, the ability to vaporize that sweat and lose more through evaporation is going to increase. We can also, by increasing our ventilation rate, the air we're blowing out is much hotter than the environment generally. We can dissipate some heat that way. Again, through evaporative cooling, we are doing a lot more. But there is a lot of animals that is their main heat loss mechanism, is panting. And also, again, as the environment is less moist, we can lose more heat that way. So if there is no precipitation on you, if it's raining and it's humid, you're going to have a hard time cooling for the very simple reason that it's already raining on you. It's going to be difficult for you to have that sweat increase that heat loss at all. Generally, if the air is warmer, it can take on more moisture, which is part of the reason there's a lot more thunderstorms. And again, generally, if you're underwater, this is where you have to be very careful. So a lot of times with like Ironman events, for example, when you are doing something that's generating heat and you're swimming in a certain temperature of water, so I think the cutoff for wetsuits, they stop letting you do wetsuits at I think at about 70 degrees of water temp, because when you're in the water, there is no air moving past you. There's going to be no evaporation because you're completely covered in liquid. And if that water is hot enough, you can't actually dissipate enough heat. And they actually start banning wetsuits at some levels, and as the water temperatures get a little bit too warm. And as I've said on all these ones so far, any things in reverse are going to have the opposite effect on this one. So again, increased moisture is not going to help evaporative heat loss. Increased moisture in the air. All these factors that we've talked about, if we flip it around, they would have the opposite effect on that evaporative heat loss. So what we're going to talk about at the very end one here is we're then going to talk about heat storage and kind of this balancing act between creating the heat and the ways we're dissipating it. And if, again, those ways that we're dissipating it, if also we're getting a lot of radiation and it's very high humidity, that means some of those abilities to lose that heat on that end of the scale are lost. So either we have to generate less heat or we're going to end up storing it. So I will talk to you next time.